All right, so we know that capacitors store electric potential energy, and they do that in the form of the electric field. And they do that by separating charges between two parallel plates. That's the model we've built. So the symbol, the electrical symbol for a capacitor is actually two parallel plates. Right? We have wire coming in, two parallel plates, and a wire coming out. There's no actual connection between the two, as we know. It can be filled with a dielectric, but we don't show that. We just show this as a symbol of a capacitor, whatever structure that capacitor takes. So the way this works is if you establish a potential difference across these plates, what's going to happen is you're going to pull electrons from one plate and leave that plate overall positive. And you're going to be pushing electrons onto the other plate, and that plate will become overall negative. There's an electric field that gets generated inside. That electric field stores energy, and then if we disconnect this capacitor, we now have some stored energy. We can then take it somewhere and use it. It's just like a battery, only it's a lot less regulated than a battery is, which is why we don't use capacitors, but we do use batteries for a couple of other reasons too. Now, so if we do this, then we know that across these two, there is some potential difference, which I'll call potential difference of delta V C, the capacitance. Okay? And that is going to be equal to the charge Q divided by the capacitance C. This is on your formula sheet, actually. It says exactly that. So the amount of charge that's built up is going to be dependent on the potential difference and also on the capacitance. So those three are related to each other in this mathematical formula. That's going to be important because remember those rules for Kirchhoff, the loop rule, that potential differences around the loop have to sum to zero. That's a conservation of energy term. That's going to be important, this reminder right here, because an uncharged capacitor has zero charge, and so if you plug a zero in up here, you get zero potential difference. So an uncharged capacitor will have zero potential difference across it. But a fully charged capacitor will have some potential difference across it, depending on what battery you've hooked it up to, so some maximum value. All right, so let's take a look at a simple RC circuit, a circuit with a resistor R and a capacitor C, and we'll take a look at what happens to that circuit over time, because that's the issue here with capacitors, is they behave differently in the beginning of a problem and at the end of a problem. So let's take a look at that. So I'm going to start off with some battery or power supply providing some EMF, E, and then I will have a switch so I can turn it on and off. I'm going to have a capacitor, C, and then a resistor, R. And this resistor could be a light bulb. I'm just giving a general resistor here, R, and some capacitance, C. So here's our very first and a very simple RC circuit. Right? Now with the switch open, clearly nothing is happening. We have a potential difference provided by the battery, right, which is script E, right, whatever that voltage is, maybe 9-volt battery, maybe you have 3 volts, so 2 AA batteries together, who knows, but that's the potential difference there. We have no potential difference across the capacitor because it's uncharged. We have no potential difference across the resistor because there's no current flowing. And remember that the potential difference across a resistor can be given in terms of Ohm's law. So this is the potential difference across the resistor, is I times R. Now, this I is 0 because there's no current flowing, which means the potential difference must be 0. All right? So that means the entire potential difference from the battery is then lost in this gap right here across this physical switch. So if you were to attach a voltmeter right here, that voltage that you read would be minus the potential provided by the battery. That's what you'd get, minus script E, minus 9 volts, minus 10 volts, whatever you're reading. So that potential difference provided by, measured by this voltmeter right here would measure the voltage from the battery. All right. Now, let's say that at time 0, we close that switch. All right? So, at time 0, what is happening? Well, the capacitor at time 0 has no charge. It's uncharged. Which means, as we just said before, the potential difference, which is equal to Q over C, must also be 0. right? Now this switch is closed, which means it's just a bare wire, and so that means we have no potential difference across wire. We assume wire is a perfect conductor in all of these circuits. That's a model. It's one of the limitations of our model. Not perfectly accurate, but it suffices. So then we have no potential difference across here, no potential difference across here, which means all of our potential difference must be lost, right? The potential we gained must be lost by this resistor. So if we were to sum up all of the potential differences for our loop and set that equal to 0, we would have some potential difference from the battery, plus some potential difference across the capacitor, plus some potential difference across the resistor. Now, this notation right here, delta VR equals I times R, this is really just talking in terms of magnitude, as is this one here, right? If I were to measure this potential difference one way versus the other, red on one side versus black on the other side, I would get a positive or a negative value. So when we're recording these and setting it equal to 0, well, remember that we're actually dropping in potential. That's why we sometimes call it a voltage drop. And so this one, the potential difference across the capacitor, we know is 0 because it's uncharged, which means that the potential difference across the resistor is going to be equal in magnitude, but negative, to the potential provided by the battery. And that means the current flowing is going to be equal to the potential provided by the battery, divided by R, according to Ohm's law, and we'll just say that this is the maximum current. It's basically just as if you have one resistor wired up to one battery, it's exactly what you get. So, an uncharged capacitor in a circuit behaves just like a chunk of wire. There's no potential difference across it. So, at time 0, the capacitor is basically a bare wire. Okay? Or sometimes referred to, if you read it, as a short, meaning it's just wire. There's nothing else. Like a short circuit is wire connecting two ends of the battery. This is just a short, is what they call it. So, we can essentially ignore it when we're talking about potential because the potential difference across it is 0. So it's just as if there's wire there and nothing else. Okay? But let's take a look at what happens after a very long time. So if t is equal to infinity, or if you read problems, it says after a long time. Well, after a long time, the Q is not equal to 0. Is it? What we've done is the moment we throw that switch, we have some current flowing. Well, we can't get electrons to move all the way around the circuit. They're actually going the other way, right? We can't get electrons to move all the way around the circuit because there's actually a physical gap inside that capacitor. So what's happening is electrons are being pulled off the top plate, moved around, put through the battery, and electrons are being pushed by the battery through the resistor, and then back onto the bottom plate. So we are building up positive charge slowly, right, over time as that current flows. So every moment that the current flows, every moment we have electrons that are moving, we're building up more and more and more charge on the capacitor. The first electron to go, now the charge on the capacitor is 10 to the negative 19 coulombs. The second charge to go by, now it's 3.2 times 10 to the negative 19 coulombs. The 20th electron, the 5,000th electron, the billionth electron, we're starting to build up a sizable amount of charge as we get more and more electrons moving through the circuit. But think about what's happening to the potential difference across the capacitor as the current flows, as we build up more charge. As Q gets bigger, so does the potential difference. And according to this relationship down here, if this potential difference starts getting bigger, the potential difference across the resistor starts getting smaller because they have to be shared. They have to add up to the battery's potential difference, the EMF provided by the battery. So as this potential difference across the capacitor goes up, the potential difference across the resistor goes down. But the potential difference across the resistor determines the current through the resistor, according to Ohm's law, and as the current goes down, the rate at which you're charging up the capacitor goes down. And so it starts off really fast, because the current is maximum right at the very beginning, but then the current gets decreased as the potential difference across the resistor goes down, and that happens because the capacitor is being charged up by that same current that is flowing through the resistor. the current goes down, the potential difference across the resistor is affected, right, at the same time, which means the rate at which we increase the charge on the capacitor goes down. This is an exponential function. The mathematics of it are outside of AP Physics 1 and AP Physics 2. You can take a look at AP Physics C if you want. It does talk about it a bit in your textbook, and it talks about a time constant. That's not on the test. What we're looking at is basically the steady state condition. What happens right at the very beginning, and what happens after a long time. Basically infinity. All right, so at that point, the current is going to go down and down and down because the potential difference across the capacitor is going to go up and up and up because the charge on the capacitor is going up and up and up. That's going to happen until we get no more current flowing, and the only time we can get no more current flowing is if the potential difference across the capacitor is equal to the potential difference provided by the battery, that EMF. Think about why that is. If there's no current flowing, what's the potential across the resistor? It must be 0. So if there's no potential across the resistor, that means all of the potential provided by the battery, that EMF, must be across the capacitor. That's our final steady state, is when the potential difference across the capacitor is equal to, in magnitude at least, the EMF. It's going to be negative if you measure it the right way, because it's dropping in potential. But that's what we get. That's what we get. That's our steady state right there. And so if we take a look at our loop, right, sum our potentials around a loop, and set that equal to 0, that's Kirchhoff's loop rule, then what we get is that the EMF plus the potential across the resistor plus the potential across the capacitor must be equal to 0. We know that the potential across the capacitor is equal and opposite to the potential from the battery, the EMF. And so we get that the potential across the resistor must be 0, which means that the I is 0. And if you have a circuit that has no current flowing in it, that's like a broken circuit. And so a capacitor that's uncharged starts off like a short, but a capacitor that is charged behaves like an open circuit, an open switch. So capacitors basically behave the opposite of a switch does. When the switch first is closed, then that capacitor basically behaves like a bare wire. But over time, it's like it opens up a switch, a gradual switch in a way, but it opens up that switch. And so at time equals infinity with a fully charged capacitor, then the capacitor is an open circuit, or behaves like an open switch. It goes from being a short to being open, a break. Think about what's going on over time. This current starts off at some maximum value, but then it slowly decays to 0. If you were to look at this graphically, you would find that the current over time is going to start off at some max value and then decay exponentially to 0, following a very specific pattern. The charge on the capacitor is going to behave exactly the opposite way, starting off at 0 and increasing exponentially to some maximum value. Q max, where that Q max is going to be equal to the EMF divided by the capacitance. And then the potential difference, which is proportional to the charge, that potential difference is also going to increase the same way, the potential difference across the capacitor. Right? If this were a light bulb, you would start off with maximum brightness, and it would dim to 0 over time. Let's see that. I have set up here a circuit, and it looks a little complicated, but we have power coming out of the power supply, going into the ammeter, which is measuring current, goes through a switch, there's our switch, goes into the light bulb, and then connects through to this thing over here, and that thing over there is a capacitor. Now this is a, focus, can you please? There we go. So this is a capacitor that we got. We have a big set of them. Here's one, and this one is, they're called ultra capacitors or super capacitors. This is actually a 4 farad capacitor, which is ridiculously large. Sorry, my hands are very dry. I'm washing them a lot lately. So the 4 farad capacitor is large. This one is actually 1.5 farad, which is a very large capacitance. Usually we're talking about micro or millifarad, or sometimes even nanofarad for some of the small ones. But these are newer technology. They work similar but different to what we've been studying, but it's just, they're fancy. They kind of work by magic. But they are capacitors. They work fundamentally the same way in circuits. So we have that, finally, that the circuit is connected through this black wire back to the power supply. So what I'm going to do is, if I throw that switch, according to our learning on the board over there, then what we should see is that the current starts off at a maximum value and then slowly decays down to basically 0, but it should take a really long time because it's exponential, and exponentials actually take forever, so it's not technically ever 0, but small enough we can't measure it. Alright, and we should see that visually by having this light bulb start off very bright and then get dimmer and dimmer and dimmer over time. And the bigger the value of capacitor that we have wired up over there, the longer it'll take, because the time, the equation that determines how much time it takes depends on the value of the capacitance. Alright, so let's get down nice and close for this. So if we can see both the light bulb and the current at the same time, ideally, be able to do that. And then we'll turn this on and we see bright. And then it slowly and steadily gets dimmer. And the current goes down. And down. And down. And now you can all go to sleep. So it's small enough current now that the light bulb doesn't even look like it's lit. I can't visually tell that it's on, but the current is not, strictly speaking, 0. But there we go. Now, what we're doing right now is we're charging up the capacitor. So this, we can't see anything special about it, but it's getting charged. And so there's a charge being separated in there that's storing energy in the form of electric field. So if I were to disconnect this circuit and then take my capacitor and wire it up across my light bulb, I should be able to discharge the capacitor. It stored energy, and that energy can be used to do something. Now, it doesn't store a huge amount of energy, and the light bulb consumes a lot, relatively speaking. And so once I connect this, then we should find that the light bulb turns on, right, because there's some potential difference established across it. There's some potential difference across that capacitor now. It's charged to some degree. And then that potential difference gets transmitted across this light bulb. A potential difference across the light bulb means that current flows, and current flowing means it turns on. But as soon as we reduce, or as soon as we have some current flow, we're going to reduce the charge because we're returning the charges to the original locations. And that means that the potential goes down, which means the current goes down, and so the rate at which the current flows is steadily decreasing over time, but the current is decreasing, which means it gets dimmer and dimmer and dimmer and dimmer. So let's plug this in and see if we can do that. So there we go. The light bulb started off bright and then got dimmer and dimmer and dimmer. And right now the only thing in that circuit is the capacitor, separated from everything else, electrically speaking. Okay? So, that's what we got.